Okay, so this is the end. There's two more problems from the last set of lecture notes. I couldn't get to them, so wasn't going to rush it. Describe how the value of delta G can be used to determine qualitatively the spontaneity of a reaction. Well, we know already that if it's negative, then it's spontaneous. If positive, it's non-spontaneous, but there's a little bit more to it. If delta G is a large negative number, this means spontaneous. And when they say large, that's qualitative. That's what they're saying. It's just not pure exact numbers. Because the range, and let's see what they say, more negative than about negative 10 kilojoules. So that means that if you have a delta G that's more negative than that, you should expect it to be spontaneous, where you can actually see something happening. If delta G is a large positive number, and so about 10 kilojoules, positive 10 kilojoules or above, then it's non-spontaneous. And then when delta G is small, somewhere in that range between minus 10 to 10 kilojoules, plus 10 kilojoules, we should expect to see significant amounts of both of reactant and product at equilibrium. So we have the three possibilities here. When it's large negative, we should expect mostly products. When it's the large positive value, mostly reactants. And then when it is somewhere between minus 10 and 10, we should expect to have observable amounts of both reactants and products. We like things, you say, well, but you said that delta G is negative, then it is spontaneous. Yes, but there's also the reverse reaction. We have that equilibrium that goes on at all times. So when we get somewhere around this area, then we're going to see that equilibrium. We're going to see that uncertainty in which way the reaction wants to go, and then we have more stuff to do. When delta G is a gigantically large number, it's negative 800 kilojoules per mole, we know we get nothing but products. When it's a gigantically positive number, it's plus 1,000, then the reaction doesn't go at all. But when it's in between here, then we got that wishy-washy area where we have to study the equilibrium amounts. Then the last thing here, maximum work related to delta G. The maximum work that you can get out of any system is delta G. Now, and this is why this term was invented. Delta G, we already had the equation for the spontaneity of a reaction. That was already known, that delta H minus T delta S is less than 0, then that's spontaneous. So it seemed like this delta G was just latched on for no other reason than to just come up with a new term. But it turns out that the delta G is the maximum work that you can get out of a system, which was originally why thermodynamics came into existence, was to answer that question.